Strings and Pulleys, Part 3. What we're going to do is another example that's just slightly more complex than the ones we have done so far. So in this situation, we'll start with a 10 kilogram block sitting on the tabletop, and we will put in a couple of little pulleys here and here so that we can hang 5 kilogram block off of one side, and off the other side we will hang 8 kilogram block. And we will have a coefficient of friction. I'll just write it sort of up to the side here to remind us of 0.2. Now we have two ropes, so we have two tensions. There'll be a tension in the rope over here we'll call T1, and the tension over here we'll call T2. And so our goal is to eventually find how much tension there is T1 and T2 on them both. So that's what we're after. So let's start by drawing in sort of a free body diagram. We'll draw some arrows. What we have are some gravity forces, Ft, which is mg. So in this case, 5 times 9.8, which I think is, 49 newtons. Right? Then we have over here, we have another force of gravity, Fg, 8 times 9.8, or about 78.4 newtons. And then in the middle, a force of gravity. And I think we've taken to subscripting these. So this is the 5, this is the gravity on the 8, and this is the gravity on the 10. So we keep track of them all. And this is 10 times 9.8, or 98 newtons. Because that 10 kilogram block is sitting on the surface, there's also a normal force associated with it, so we'll put that up here. And then we have our tension forces, which are sort of in the ropes, pulling on the blocks. T2 would pull like this, and T1 would pull like this. So those are our tension forces. And what we said in the previous video was we would consider the entire system first. So our first step is to look at the entire system and try to decide if we can figure out something about how it's accelerating. Look at the entire system and see if we can't find out something about the acceleration. Right? Okay. If we look at the entire system as a whole, what we're going to do is we're going to change our reference frame. So we're going to look at the up and down, but then we're going to sort of look at our x as if it's a clockwise, counterclockwise motion. So any forces that are making this system move in a clockwise fashion would be considered positive, and any forces that are making it move or pulling in a counterclockwise fashion would be considered negative. But our up and down forces on the y-axis are kind of staying the same. So the y-axis is really just for the 10 kilogram block. So the first thing we can do is look at the 10 kilogram block, try to get an idea of the friction and the normal and its own gravity, because that's the part that is going to be stopping or working against the gravity that's moving this system. Okay, so I'm kind of doing a little F net Y here. And in this, we realize that there is a normal force plus a gravity force on the 10 kilogram block only. And we know that the 10 kilogram block is not going to accelerate in the up or down direction. It's not going to move this way. If it moves at all, it will move along the x axis. It will slide sideways. So this will be a 0 acceleration. And the normal force will stay there. And this will be mg, or negative 9.8. And so we see that 9.8 newtons, 98 newtons, my mistake, 9.8 times 10. So 98 newtons is the weight of the block. It's also, in this case, the normal force. Okay, and that's the normal force that's acting on the entire system, because the 5 kilogram block and the 8 kilogram block have no surface to provide a normal force, so that doesn't exist. Okay, so now we know that. Let's look at our forces sort of sideways. If I look at the entire system as a whole, I can redraw the picture as one big giant mass. 8 and 5 is 13 and 10, so it would be a large 23 kilogram mass on the whole system. If I look at what's trying to move it in a clockwise direction, now remember, when we consider the whole mass, we don't worry about the tiny little forces acting in between, like the tensions. So when we consider the entire system, the tensions in the rope are internal forces, just like the forces between the molecules of anything that we push or pull. So we don't look at those. We're not looking at the green arrows. So what's making this sort of move in a clockwise-ish kind of direction? Well, if I draw that here as a force, we have the force of gravity on the 5 kilogram block over here, which is 40 newtons. That's a 5, not an S. 49 newtons, trying to make the system go sort of that way. On the other side, we have something trying to make it go the opposite direction. It's the weight or the force of gravity on the 8 kilogram block. So it's Fg on the 8, and that is 78.4 newtons. The only other thing that's acting is this frictional force, right? This frictional force, which I was sort of working at over here. The force of friction is going to be acting somehow. We have to figure out which way it's going to act. Well, clearly the 78.4 is winning the tug of war, and so if this moves at all, it would have to move in a sort of counterclockwise direction. The heavier 8 kilogram block would float that way, which means the frictional force is going to have to be acting against that. So I'll put my friction over on this side. So this is what's happening in my X and Y, or my X sort of reference frame. So let's write down what's going on here. F net X. F net in this situation is 78.9 to the left, or in the counterclockwise sort of direction, right? 49 newtons sort of to the right, and the force of friction that's going to appear acting sort of in a clockwise way, preventing that motion. The F net will be MA, negative 78.9. I guess we could add those numbers together. Pretty much. Okay, and then mu Fn is what we put in here. That's why we did this little bit of work up here, because that's our normal force. So we're going to bring that down. And we have a mu is 0.2. So if we do a little bit of math, the mass of this is 23, so we get 23A equals, and let's see, 78.9, and then 49 is going to be pretty close to 30. It's about 29.9, right? We could put 30, but that's fine. Now the friction is 0.2 for the coefficient, and the normal, we had it up here, 98 newtons. So I'll put that in. Now, the friction is contributing to clockwise-ish motion, or at least it's trying to prevent counterclockwise. So that would be a positive number in this particular case. And if we keep simplifying this until we get to an answer that we want, 29.9, this would be 19.6. And so the difference there would be 23A, and that's looking like 10.3. So we still have a negative number, right? And if we do division, divide everything by 23, we get about 0.44 meters per second squared, and of course we get a negative number, and that's what we want, because our original assumption was that this would move, the 8 kilogram block would win. So we're getting this kind of motion, that's counterclockwise-ish, so the negative acceleration is what we want. So far so good? Did I make a mistake? Say that louder. $78.9. It's 70.4.
Yeah.
Did I have that wrong?
You like.
Oh, I see. It's 78.4. Okay. Well, that'll make a small difference. We should fix it. It's 78.4. You're right. Which changes this a little bit. It changes our decimal ever so slightly. So what should I have here? 8.4. And so it's 28.6. Is that what it is? Or what's that subtraction there? $29.4. Okay, 29.4. Sorry about that. But we have to get the right number. Doesn't change our method. Our method is still what we want. We just have a little error to fix. So instead of 10.3, 29.4, it's 10.2, right? And this comes out to what? 9.8? This is?
Yeah.
Oh, isn't that cool how it came out to 9.8? 9.8 negative. So instead of 0.44, our acceleration is going to be what? 4.3. So changes everything just slightly. That's a good point. We got to be correct. Okay, so we're happy with that acceleration, and that's the acceleration of the entire system. Now, what I want to point out is a dangerous thing that could happen. I made the coefficient of friction fairly low, 0.2. What if that coefficient of friction was higher? And let's just pretend for a moment that it was 0.5. Let's look what would happen to our math. I'll write it down beside here. How would it change? Well, if it was 0.5, this number would change right here. So we would have 23a, we would have negative 29.4, but then 0.5 times 98 is 49. So we would have plus 49. Now remember, this last number right here represents the force of friction. So I'm going to put a circle around it. Okay? What? What would be 47? 0.5 times 98? I'm sure I got that one right. It's 49 newtons. Now, watch what would happen if you put in this 49. Now, Danielle, why don't you figure out 49 take away 29.4 for me? 19.6. Positive, right? Positive. If you weren't aware of what was happening and you just merrily went on your way and did your final calculation here, you would see that, let's see, 19.6 divided by 23, you would get, did I do that right? 19.6 divided by 23, 0.85. And you would say, there, I got my answer. Now, look very closely, but this is positive, and this original answer over here was negative. We said that the answer had to be negative because the block has to slide sort of counterclockwise. Look at the original picture. Our answer of positive with that higher friction tells us that somehow it's going this way. But that's impossible because the 8 kilogram block is got more weight than the 5 kilogram block. So what's happening here is that you're using the friction not as a reaction force, but as an action force. You're assuming that the friction is going to somehow pull that block, and it doesn't. What you have to realize is, at any point in any net force equation, if the amount of friction that you have worked out is larger than the total amounts of all the applied forces, then this is not true. and the object will not move. Friction wins. Friction beats the applied forces, right? So you would have to be aware of that. And if you've got a positive answer for A, hopefully, because you're not just memorizing the solution and crunching out numbers, you've thought it through and you're already thinking, I have to get a negative A, because I have to go counterclockwise in favor of the 8 kilogram block. We know that that has to happen. This cannot happen. So that should be an alert for you. So be careful with friction. Remember that friction, when we calculate mu Fn, that's the maximum amount of friction. But the friction only pulls with whatever force it needs to. It counteracts applied forces as a reaction force. So it may not pull. What would happen in this case is if there was an applied force of 29.4, then the friction would pull back with 29.4, causing it to not move. Because 29.4 is well within the limits of how much the friction can pull, can stop. Okay, now having said that, it's fairly easy to get the tensions. To do the tensions, now we look inside, and for T1, we'll look at the 8 kilogram block. It has a tension force pulling up, and it has a gravity force pulling down. And so the gravity force was 78.4, and we're trying to find this T1 value. So F net equals ma, right? In this case, it's equal to T1 plus gravity. And so we have ma 8, and we know our a is negative 0.43. And that means that T1 here, and then we have, now remember, in our reference frame, this number is contributing to clockwise motion. So although it looks like it's down, we have to remember that we are considering that as movement in a positive direction. Yes, the negative here is the counterclockwise acceleration, but this force is pulling in a clockwise direction, isn't it?
No, it's on the left side of that kilogram box.
Oh, you are right again. This has not been my day. I'm going to have to remake this video, I think, because this is about the 10th mistake I've made. I should have stayed in bed this morning. Right. That is movement this way in our reference frame, so it should be a negative number. It's a good thing you guys are here. Okay, let's do some math. Let's clean this up, at least the math we can do, or we can try. Let's see, 3 8s are 24, 32, 33, 3.44, right? Okay, good, 3.44. And then T1, and it will be negative, right? Negative 78.4. Bring it to the other side, 3.44 plus 78.4 equals T1. So T1 is about 75-ish newtons, right? So let's just say 75-ish newtons is the value of T1. Now we got a positive number. Does that make sense? It does, because T1 is pulling up right here, and in our reference frame, that was causing motion in the clockwise direction. Okay, and then to get T2, we do the very same thing, except we do it with the 5 kilogram block. And we have the tension, T2, and the gravity. And this time, this is the one that I was thinking of. This gravity force of 49 newtons is going to end up being positive, right? F net equals T2 and gravity. That's all there is. So we have M5, 0.4, oh, I better put the negative, leave room for the negative in there. Negative 0.543 equals T2, and in this case, plus 49 newtons. This is what I was trying to say before. Now it makes sense. Remember, this looks like it's down, but it's clockwise motion. So we leave it as 49 positive. So 15.15 negative equals T2 plus 49. In this case, then, we have negative 2.15 minus 49 equals T2. So that's about 51-ish, 51.15 if you want. And it's a negative number. And that makes sense, I think, because T2 is pulling up and it's contributing to motion that is sort of counterclockwise in our reference frame. So despite our algebra mistakes and our bad math, we've managed to crank out the appropriate answer. So once again, then, just to review, let's look at the overall solution so we know what to do. First, we find the acceleration of the entire system, which is what we were after right here. And we had to think a little bit about how our friction would have acted. Once we figured that out, we put it in, we did our net force equation, and we found that the acceleration of the system was here. And we pointed out the fact that in a different question, it could have turned out that this object wouldn't move. The friction might have been enough to just hold it there, and the 8 and the 5 wouldn't have been heavy enough to make it move. And we saw how we have to alert ourselves to that and double check. The general rule of thumb is, if friction is greater than the sum of your applied forces, it isn't going to move. And then once we did that, we looked at each block individually, remembering which side of the table they were on so that you don't make the mistake that I made. And we put in our numbers, and we got our two tensions, 75 and 51-ish. Notice the tensions are different because it's two completely different ropes, and each one is hooked to a completely different mass. And that's the end of that.